Normally I work as a data scientist in if research in Poland, but we are doing projects mostly for mother Zettafox company in Paris. So basically in this talk I will talk about toy examples, but motivation was the real business case that we solve. So yeah, I will start with some. Okay.
I'm sorry.
Okay. With short motivation, and since I am a physicist, I will talk a little bit about mathematical background of the problem, then how to solve it intuitively in something Haskell-like, and then I will give some examples. The code is on GitHub. I pushed it today, so there will be some live coding demo too. Okay, so first the motivation. What's the problem, basically? I mean, we like Haskell. I mean, I like Haskell. People hate me for that. Because we like pure functions. Yeah, so I mean, pure function is a function that does not produce you any side effects, like squaring the number. The thing is that when we want to have a function that returns the random value, it can no longer be pure. Well, because the pure means that the same input produces the same output. The random means that we randomly choose something, so the output changes. Well, of course, we can use, for example, IO monad. So do our random computations in some monad, for example, IO. But, well, we like pure functions. Yes, so it's not good. But, well, okay, but one might say that, well, the random values are random, but the random generators are actually pseudo-random generators, so they produce deterministic result if we provide also the random state generator with other arguments. So we could implement our flip coin function in a pure way by adding the random generator seed, whatever it is, depending on the random generator. But, well, it's not so nice because then we need to add additional arguments, we need to remember to pass those arguments and so on and so on. Yeah, but, well, we can, for example, hide this seed in state monad or whatever else, but that's again means that we need to use, I mean, well, we could, but somehow it is still not so elegant. And moreover, that would not work if we, for example, have a source of true randomness, like a device that we connect to our computer that we can connect on dev something and that produce our real random numbers. Then we will need to use IO monad anyway. Okay, so well, on the other hand, mathematicians like pure functions too, and they are quite good at working with randomness. I mean, they built the whole probability theory about the randomness. So somehow they solved this problem. So how did they do that? I mean, how they hide this random outcome of the experiment, which is inherent in any kind of random something. So for that, I need to talk a little bit about mathematical background. So that will be a short recap of probability theory. This is not important. This is not essential to understand everything that I want to say. This is more about building intuition, because, well, for me, the main advantage of using functional programming is the fact that in functional programming, my code looks more like the way I solve the problem in my mind. Not more like me transforming my way of solving problem into the code that is understandable by the computer. So first, my understanding of the problem. So the probability theory. So the probability theory starts with definition. We are in the realm of mathematics. So what is the probability space? Well, first we say that we have some set. We call it sample space. And the outcomes of this random experiment we don't know how to describe actually, we don't want to describe it, are the elements of this set. That's all we say at this moment. Then we consider certain subsets of this set. This is a technical requirement actually. If we have a finite set, we can take all the subsets. So let's think about it, all the subsets of this sample set. And we call them events. And the third element is the probability measure, or probability function, or probability distribution, depending on exact technical details. So a kind of function that will take these nice subsets and assign them number which is greater than 0, because we want to say that that's the probability. That sum up to 1, and this means that it sum ups to 1. So the probability that we get any kind of the outcome is 1. It's certain. For sure we get some outcome. And the kind of technical requirement that if we have two events that don't overlap, their probability sum. I mean, in this picture, to help the intuition, the omega is the set of those points. Each of these points we call the elementary event. These nice subsets are subsets of these points. We call them events. And the probability function assigns numbers to those events, which we interpret as a probability that such event occur. I mean, event occur if in the random experiment we get the result from that set. So that's how mathematicians understand probability, in short. What they do more? I mean, this is kind of not much in here. Yeah, I mean, in particular, we said we have some set. Mathematicians don't like to work with some set. Mathematicians like to work with sets with certain properties. So they introduced the notion of so-called random variable. What is a random variable? Random variable is again a function. Mathematicians love functions. Which is from the sample space to some set. Well, exactly not some set. I mean, usually the set has to have some structure. For example, the real numbers, for example, a vector space, for example, any finite set, something that is meaningful for a problem. Okay, and we can denote the set of all random variables, so the set of all those functions by this R over omega. And when we have a random variable, we can produce a number which we call expected value of the random variable, at least if x are the numbers. So, well, basically what we do, I mean, to be precise, we integrate the random variable over the sample space, but if the sample space is finite, then actually it is something very simple. This is the sum. And so this is actually the average value. I mean, if we randomly sample, then we compute average. That's it. That's what we should get. So the expected value tends to the average value of the actual experiment that we make.
Could you explain again what is R? R on omega set of all random variables?
Yes, this is the set of all random variables, so the set of all functions from omega to x. I mean, they need to satisfy all measurable functions, and x needs to be measurable space and so on. So let's forget about the technical details. If we have a finite set,
then the other part of this sentence on omega EP, like what is EP?
This is from the previous slide, the probability space. Oh, sorry, too much. It lags. Okay, this is it. Omega EP.
Very nice family and the function. Okay.
So that's what we call the probability space, probability model. Okay, so the expected value, which is basically...
P is the probability, right?
Yes, P is probability. it should be small p here. I mean, in the next version I change it to small p, but not everywhere, so sorry. Small p and capital P is the same here. This, of course, depends on the random variable, but actually it also depends on p. Yeah? And if we can write it this way, then we call p of x the probability distribution, or here also. So actually we can think about, since it depends on p, here we can consider a set of all random variables, so we can also build a set of all expectations, I mean the expected values, if we change the p, which is a function here. Yeah? So we have two sets, very abstract sets. We have two sets of the functions. Well, but we like functional programming because functional programming likes to abstract things. So it's not worrying us yet. The thing is that those two sets, the random variables and all expectations, this is actually totally sufficient from the mathematical point of view to describe any probabilistic model. And intentionally, I did not write omega here, because we can describe any probabilistic model actually without even referencing this omega. I mean, those sets, the set of the functions, have certain structure, which we can actually describe also very abstractly without referencing to the omega. And this is equivalent to the probability model. So actually, mathematicians know how to get rid of omega, which is our problem too, because we don't want to explicitly ask the random or pseudo-random generator for the values. So that's the idea. The solution is random variable, basically, because actually this can be derived from R mathematically. Okay, so how to express this idea? First, in something that will be Pseudo Haskell. Because I don't want to get into details of the implementation, also because I never analyzed this implementation of the library that I'm using. But the idea is around that, like that. So we know that the random variable is the solution to the problem of forgetting about this omega. So our basic type will be random variable. And for this motivation, building this intuition, we will think of random variable as a function from this certain set omega to some other type, so the other set. Yeah, I mean, if we don't go into the details, we can think about types as sets. So this is more or less equivalent to what the mathematical part was saying. This is actually a functor. I mean, this type is a functor. And this is a definition. And why? I mean, it's very clear if we substitute for rvar, the actual type. Yeah, so, I mean, rvar is supposed to be this. So we need to implement function like that. So function takes, so we take a function from A to B. We take a value which is a function from omega to A. We need to produce value which is a function from omega to B. So there is only one way to do it. Quite obvious. We need to compose it in that way. Yeah. So RV is this function. So it's from omega to A. F is from A to B. So we chain them. So in the end, we get from omega to B. That's fine. And the functor laws are verified is quite easy. First, this is that fmap identity is identity. So we substitute the value identity function. We can cancel out. That's true. The second, that it's composed nicely. It's again a matter of rewriting things. So nothing really complicated. Maybe let's not stop on that for too long. So. So this is the left-hand side, the right-hand side. We just substitute by the definition. We end up with the composition of those functions. Composition is associative, so it's okay. So random variable is a functor. it's monad 2. But for that we need to abuse a little bit Haskell, actually. I will explain this in the moment when we will need it. Okay, so pretend that you don't see it. I should have hide it. So in the monad we have two functions that we need to implement. The first function is embedding a value in the monad, pure or return. Let's choose the return. So basically, well, what we need to do, we need to, from the value, we need to produce a random variable, so the function, but from the one value, the only thing that we can do is produce a constant function. So we produce a constant function. It makes sense because from each value we can produce trivially random variable. That is, whatever the outcome of the random experiment is, we choose that particular value. That's clear. Now the bind. This is the tricky part, a little bit tricky part. So let's see what are the types. So we are getting random variable, which is a function from omega to a. We are getting function that, depending on the value of a, returns the another random variable, so function from omega to b, and we need to produce random variable. Actually, what we can produce is something like that, and we can produce it in that way. But then we observe, well, actually, this is the result of the observation that the type of this composition is omega to b. Yes, because we chain this function with this, so they chain at a, so we have omega to b. But because of the carrying, omega is a pair. But the pair means that we sampled our sample space 2 times, and we can repeat it. Actually, 3 times, 4 times. So actually we were wrong in our definition of sample space, but it doesn't matter, at least for the intuition, because if we have a sample space, which we can sample many times, and that's the assumption, if we wouldn't have, then that would mean that we can produce only one random variable. That's not interesting. We can as well say that in the first place, our sample space was a set that can produce us sequences of random variables of arbitrary length. So this is basically what this this definition intuitively says. So as I said, this is abusing notation. That would be probably possible to implement it directly, but definitely that wouldn't be at all effective. But I mean, conceptually, I hope it's quite clear. Yeah, that's the pair of that we can sample many times, so produce sequences. And if we can, then basically that's the definition of monad instance for the random variable. Okay, so well, if we have a monad, then we can do really various things with that. And actually, by all practical means, we can build very complicated computations with random variables without referencing to omega, so the way of sampling, by just using the monadic interface of that. And at the end, we sample. But we sample when we want, where we want. Okay, and the biggest advantage of that is actually, at least for me, the mental model of that. That is, well, that would be probably quite equivalent to the fact that we can work in a state monad and so on and so on. But with this intuition, I know that the monad I'm working with is the random variable, and I'm thinking about them as the random variables. And I build solution thinking about them as random variables, and as I hope we will see in examples, it really simplifies the way we reason and the way we reason, the way we design the code that uses the randomness. So now we are starting to doing real Haskell. So all that is implemented in random foo package, and 2 packages that it depends on. So the basic type is the random variable, defined differently, but it has a monad instance. There is also a helper type class distribution, which is basically used to construct the random variables by the functions like that. So the standard uniform, std uniform, is the type constraint. That it means that basically we can produce random variable with some distribution of the values. So this type constraint means, and in the end it will produce us the random variable of type A. Or there is a function that can produce us, for example, the random variable with Gaussian distribution. We will see the examples in a moment. If we have random variable, then we want to have way to produce the random number. So there are two functions which I provide here with slightly simplified types that allow you to sample those random variables. So given that we are working in monad that allows us to produce random random numbers, like for example IO monad, which can ask def random on POSIX systems to produce random value. It's from the random variable it can produce the value inside that random monad. I can use different sources of randomness. Okay, so let's see how it works in real life cases. So maybe I'll make it a little bit bigger. Well, maybe not that big. It's Jupyter Notebook. It's using Haskell R kernel. I mean, I will use R just to make some nicer plots when I need them. So just a few imports to make everything work. So here I remind those types from the presentation. So we have these functions that allow us to sample random variable and functions that allow us to produce random values. So let's try them. So let's say that I want to sample standard uniform, and I need to tell, because of polymorphism, I need to say what type I want. So it produced the standard, the random variable, a random value. If we run it multiple times, we get the different ones. The same we can do by changing the type. Again, we want a bool value. Yeah, thanks. And similarly, we can produce value with a normal distribution. But since the random variable is a monad, we can use a lot of functions that work with monads. Sure.
How does it work that you return the IO monad, but you get the toString? It's automatically evaluated, right? That's how it works? IO is the suspended computation.
Yes, I mean this works like GHCI. So it interprets immediately. Okay. It has some kind of syntactic sugar so that you don't need to do let to substitute something, but that's, apart from that, and it prints you result by default. All right, so we can, for example, using the monadic interface, we can produce more than one. So we use the function replicate, for example, to produce 10 times a sample of standard uniform of type list of double. And we have it. We could do something similar with normal distribution. Well, let's submit it. So let's sample more and plot it. So here it's why I'm using the Haskell R kernel to have access to plotting in R. So here we take the 10,000 random variables with uniform distribution, the standard, so over for double it is from 0 to 1. It should be uniform. Well, it is more or less. It's satisfactory. And we could do the same thing with the normal distribution and get what we remember from school as a Gaussian distribution. Yeah. So we 10 times draw from standard normal, so mean 0 and standard deviation of 1. Okay, but I mean, that's not that interesting actually, so let's try to build something a little bit more complex. So first let's toss the coin. So for that we'll use a built-in distribution called Bernoulli distribution, which is basically a distribution that selects between two values based on probability value. I mean, so we produce true with probability p, and we produce false with probability 1 minus p. Let's define a data type for the coin and how we would toss it. So first we can just substitute it. We bind within the random variable monad. So bind means that we are not sampling in this moment, but it means that if we sample, then that's the value that we want to get. And then based on that value, we can say that we want to have a head or we want to have a tail. And I forgot something. I forgot return, of course, because we need to return the monadic value. Okay, so we can try it. We can sample it a few times. We get different results. Well, actually, if someone is more familiar with applicative syntax, then we can make it even simpler by factoring out function that transforms as Boolean values to our coin type. Then we can write it either directly with monadic bin or with the applicative syntax. And of course we can now toss it many times, and we should expect to have similar results for both cases, head and tails, which is also the case. Okay, but that was also simple. A bit more complicated problem is so-called the Monty Hall problem. Probably some of you heard about that, but I guess not everyone, so I will just describe it shortly. So it's a kind of show, a game, where you choose one of the doors from 1 to 3. Behind one of the doors is a prize, let's say the car. Behind the two of the doors are goats, you lose. And when you choose a door, then the host opens one of the 2 remaining doors, showing the goat. Then you have a choice. You can either stick to your previous choice, or you can swap. And the question is, does it matter at all or not? So actually it matters. However, it is not so obvious, and it was confusing even for professional mathematicians. So if you don't intuitively understand why it is really better to swap the doors, then that's fine. It is not intuitive, but that's the way to do it. Okay, so let's solve this problem by simulation. So we will know. So first we will define some types. So we have 2 results, win or lose, and we have 3 doors. And this is the helper function that will, depending on where the price is and what we choose, gives us answer whether we win or lose. And this is the list of all doors. Okay, so let's implement the 2 strategies. We have 2 strategies. One where we change the door and one where we don't. And the random variable, I mean the result that we get, which is the random, is the result of the game, whether we won or not. But first of all, what is random? The position of price is random. So we choose random element from the list of doors. Then we choose one door, which is also a random element from all doors. Then the host opens the door. Okay, sorry, it won't be let. If we choose a goat, then he has two doors to open, one with a price, one with a goat. Well, anyway, he has two doors to choose from. No, not always. No, in that case, he has only one. If we choose a goat, then he has only one that he needs to open, because he cannot open doors with a price. So, but if we choose a price, then he has two, so he will do it randomly.
Sorry? Maybe you can give an example how the game goes. I think if somebody didn't know the game, they have no chance to understand.
Okay, thanks for that. So the strategy, let's say that we selected door 1, then the host, and let's imagine that the price is behind the door 2. We selected door 1, then the host says, okay, I open door 3 for you, there is a goat there. Do you want to change your mind, your decision, or not? If I stick to my decision and say, no, I want door 1, I'm pretty sure that there is a card, and I open it, I get a goat, and I lose. If I say, okay, I swap, and I choose door 2, then he opens door 2, there is a card there, I win. Cool. Clear? Okay, right. Okay, so let's go back to our implementation. So, yeah, he needs to choose one of the doors. For those who don't know, this is the difference of the lists. But not the door where the price is, nor the door which I choose. That would make no sense. So this list is either 1 or 2 element. Then this is the strategy where we do change. So at this moment we do change. So we swap, but we need to know which to which one. So we take doors and we remove what we choose previously, and we remove what the host opened. This list won't be empty, and that's the result. So we return result.
More than 3 doors?
This one? No.
Yeah.
This implementation? No. Here I mean.
Exactly.
Then I would need to choose randomly from those that remain.
You have like bounds, so it kind of assumes that it might be more than 3.
But the data door is defined for...
Yeah, this is... That was just for convenience. I mean, of course, we could try to consider generalized Monty Hall problems, but... Okay, so the result of price, and we changed. So this is the implementation. Again, I forgot about something. Not in scope? Okay, maybe I forgot the syntax. Maybe it was other way around. Yeah, other way around, sure. Nobody knows Haskell here? Nobody corrected me, or you're sleeping? Okay, so this is the first. The second one is actually even simpler. So where we stick to our first decision. The price is somewhere, we choose something. Actually, it doesn't matter if the host opens or not. We can at this moment return the result. So we have implemented two.
We have to return the choice, not the change.
Yeah. Actually, this can be even simpler, like that, with applicative syntax style. Okay, the helper function that compute how many times we won compared to trials. And then let's run the experiment. So we replicate 10,000 times strategy that we change, and we sample and compute the frequency. And we replicate 10,000 times strategy that we keep, we sample and compute the frequency. So it's clear that it's better to change our mind.
But how do you know what is the distribution in that case?
I mean, we assume that the prices are, but I mean,
assume uniform.
Yeah.
But was it somewhere there, like implemented as a uniform distribution?
Random element. It randomly chooses element from the list with uniform distribution. Actually, that's quite interesting problem, but because with 3 doors, it might happen that it doesn't depend that much on distribution. Unless, of course, you learn from trials that the car is always behind door 1. But if you don't have this knowledge, then I guess it might even not depend on that. Okay, the other example that we can imagine is simple kind of numerical approximation of the value of pi. So we will randomly choose doubles from interval 0, 1, x's and y's, and we will check if the point is inside this quarter of circle or not. Then based on that, we assume we will approximate the area of this element, I mean this 1/4 of the circle, multiply it by 4, that's equal to value of pi. So, so first the helper function that will check if 2 points are inside the circle. So that's the mathematical expression for that. This is the function that estimates area based on how many points were inside. So this is it. We're inside the circle compared to number of all points that we drawn. So how we do it? Well, let's just use applicative style, because we need to randomly choose a pair. So that's it. I did not evaluate this one. Okay. This is this approximated pi. Again, with applicative style, we multiply by 4 the result of this area function, and we sample this. So I mean, this is applicative style in IO monad at this moment. Yeah, this is because this produce IO result. So we can repeat it and get some result which won't be very accurate. Actually, well, this time we were quite lucky. Okay, let's go back to the presentation. We can go even further and consider something that is called stochastic processes, which is, well, if you read in the probability book about stochastic processes, then you can get a little bit intimidated by the standard mathematical formulation, but basically you can intuitively think about that we have some random process that takes place step by step. So usually we describe it by defining what is the set of allowed states. So in Haskell that would be a type of allowed states. So for example, let it be rectangular grid. So we have 2 integers, x and y value. And we have a function that performs this jump, this evolution of our system. So given that we are in some state, it produces another state, but it produces it randomly, according to some rules. This will depend on the exact definition of this jump function. And actually, many interesting things can be represented in that way. And actually, the machine learning algorithm that we are implementing can be represented in exactly that way. And on top of that, we can build some abstractions, like, for example, function that will iteratively run this process, simulate it. N number of times. The process, which is, this is the type of the jump function, I call it T, so this defines this transition in our process. We need to start from some point, so this is the starting point. And as the result, this is the final state. And it should be run, sorry. I did not change all the names. This is the recursive definition. This is run. Sorry for that. Okay, we can implement it too. On implementation, I did not make that mistake. So this is the same implementation that I made a little bit more polymorphic, so it's not state, it's some arbitrary type. There is also a helper function, maybe I will not go into details. It's basically the same as that, but I return the list, I return the whole history. It will be helpful. Okay, so the other name under which we can find such simple random processes is random walk. So this is this rectangular grid, this state space, and what will be the jump? Well, we will randomly we live on the grid of integers, so we randomly choose one of the 8 next integers. Can I use this whiteboard? Okay, so if we are here, we have 1 point above, diagonal to the right, diagonal down, diagonal here. So we are here and we can randomly go to one of those points. So this is what we are doing here. We randomly choose one of the 8 directions and then we modify our state. Pretty simple. I guess. And then we run this process, remembering history to make a nice plot. Let's hide it for a while. Starting from point 0, 0, we sample it. And because Haskell R does not know how to pass ints to R, we need this to transform to double, and this to get x's and y separately. And we make a plot. But I need to evaluate all that. But we have a nice plot. This is the trajectory of our random process. That's how we were jumping all the time. We can do the same for doubles. It will look very similar, but I think that this is nicer.
Can you re-evaluate this?
Sure.
A number of times?
Looks similar.
Yeah, because I did not resampled. Now it's different. And it's different. Oh, that was funny. The average distance in this case will be square root of n, number of iterations from the center. Okay, the other example, snake and ladders. Those who have kids maybe know this game and how annoying it can be. Game is pretty simple. I mean, you just roll the dice and you move your pawn, and when you hit the head of a snake, you go down. If you get to the ladder, you go up. But here, near the central point, you have a lot of snakes and very little ladders. So after 5 times, you go from here to here. You start wondering if it will ever end.
So you wrote a program to play with your children?
No. I wrote a program to convince myself that it will end at some moment, at some time.
And what's the expected value of how many?
We can compute it.
How many children we can convince?
Okay, so here I won't be doing live coding. It's late. I would probably make a lot of mistakes. So first we encode this board in a way that, well, it's a vector, and the number, if we stay at the field, is the same number. If we go up or down, then we put in the vector number where we go. So for example, there is a ladder from field 11 to 43, so that's this ladder. And here we are making the board of that, so basically those numbers are the target of the target field we end up if we enter that field. Yeah, another helper function in the style of run. Previously we had run with fixed iterations. Unfortunately, that game does not have fixed number of iterations, so it is until. So basically we check the Boolean predicate, and if it's satisfied, then we finish. If it's not, then we recurse. This will be a helper function to count our steps. So we take the function that do a jump, and current number of steps and the state and the random variable. Let's not go into details. Here is the actual step. So we randomly choose one number. Fortunately, my son discovered that we have 20-sided dice in a home. That really helps. So that's why it's K here. So we randomly choose a dice, and then we go to the place that is defined by this function. So if x plus, so our current position plus number of that we get from a dice is less equal than 100, then we jump to, I mean, we check where we end up by this. So we check what is element of the board at this designated field. If it's not less than 100, then sorry, we stay. Okay, so and the game is defined here, basically. So the type of move is without this. This is rvar. Don't be confused. This is without number of steps. So we are using this function count to add the number of steps. So the starting point is position 0 and 0 number of steps. We run until we end up at field 100, and we are interested only in number of steps it took. So the type of the game is also a random variable. As an argument is a number of sides on a dice, and this is number of steps. So let's play it a few times. 74, 102. This happens quite often. And 81 and so on. Okay, so let's draw a histogram of the values. So we repeat it 10,000 times. It will take a while. It's not compiled. If compiled, it would be much faster. But
it depends, because it's possible that you can play infinitely long for.
Yes, of course, it is possible, but fortunately quite unlikely. But as you see on this histogram, it can happen that you need to roll a dice 500 times. But the probability is really small. The average value to statistics. Okay. We need to double and from list also dot 84 moves on average. Not that bad. With dice 20, it's a bit more optimistic. Still, it can take a lot of time, but, well, not that long. And the average will be, this is the same, 33, so the average is smaller. Okay, that was an experiment that didn't work. Okay, so we can...
What if you were tossing a coin? Just go
I'm afraid that would be a cycle when I enter first snake.
Okay, yeah, that's true.
Yeah. Okay. And the real-life applications. So this concept was actually used in one of our machine learning algorithms that built what is called the classification rules. The classification rule is basically a predicate on a database that is a kind of expression that selects the rows, like a query in SQL. We have a function defined that can transform any row of a database to a rule that picks out that exactly row. Of course, it can pick out more than that row if rows are the same, but basically that's the way it works. And two rules can be combined without going much into the theory of that. Basically, you can construct the rule that, this covers some instances. The second rule covers some instances. We can construct the rule that covers instances of that and that rule. So that's the function that we have specified. And obviously, we can score somehow those rules. For that, we need a database and we need the rule. And here should be a double. Not the database, of course, so the value of the score. And the algorithm, this is simplified version, just to make it shorter, but the real algorithm is not really much more complicated. Just 2 or 3 heuristics. There are 5 points instead of 3. So we are building the final rule iteratively. We start with a null rule, so the rule that covers nothing. That's the specific kind of rule. We randomly take, and we construct the pool of rules from all instances of a database. So we take all instances, we convert them to rules. We have a pool, the set of the rules. We take randomly one of them. We combine with the rule that we had on the previous step. So if we are on the step 1, we combine it with a null rule. And then we check if the rule that we got, this Q prime, has a score better than certain threshold or not. If it has, then we accept this rule as a rule on the next, for the next iteration. If it's not, then we don't change the rule. But the rule that we drawn from the pool is, in any case, discarded. The score drops in the process, generally. The kind of score that we are using here. So that's why that kind of implementation. So this is the specification of the algorithm and the implementation. It's really straightforward. So we have a function that picks something randomly from a set, and the random variable, and the set without that element. So the step of this algorithm, which depends on a database because we need to score it, depends on the score threshold because we needed to decide what to do next, and the current state, so the rule and pool of the remaining rules. We randomly pick one element from the pool, and then we update. So what's the update function? Well, the update function means that, if Q prime is this combined rule, if the score of combined rule is greater than the threshold, then we return this Q prime as a new rule. Otherwise, the rule that we entered, this function. So this is the jump in the stochastic process. Exactly. If you forget about this, you partially apply these arguments. You have state and random variable of the state. So this is it. And then we can use the run functions that we or run until that we defined previously to implement the whole algorithm. So mine takes those two, the database and the threshold, and returns randomly the final rule. How? It runs the stochastic process defined by this step until the pool is empty. Well, we check that this set is empty. The step function is this. As I said, we partially apply this function, these arguments, and we start from the pool and the null rule. Opposite, again, copy paste. And the pool is constructed by taking all rows with positive target. There is a target column defined. We convert them to rule, we convert it to set. Really pretty straightforward. The advantage of that was that it actually simplified the code. The previous implementation was written in C and Python. Shrink factor of the lines of code was about 10, even more. I mean, it's hard to estimate because I mean the C and Python implementation. In C and Python implementation, the modifications that we make on the rules and this random sampling and algorithm, everything was mixed up, like typically in imperative languages. Here it is separated, so it's hard to really combine. But the core algorithm has something like 15 lines of code currently. And this really expressed this core concept. It was much faster. Well, not because Haskell is faster than C, but because the other implementation, because of mixing everything together, was crappy. And it was much easier to develop. Actually, it took me 1 week to rewrite this algorithm in Haskell, knowing only specification, because actually trying to understand the previous code would take me much longer than that. So
you were developing around three lines a day, yes?
That's a good result, I would say. No, there were many experiments around that also. Yeah, but I mean, that's nothing strange. Haskell to produce 3 lines of code a day.
First 15 minutes and then was fighting compiler.
Could developers write 20? Great developers write 3 spots. No, but it's not 3, it's 10, right? 50 lines in 5 days. 50.
But if you commit the work on the weekend as well.
It's 50. Oh, okay. I thought it was 15. Okay. So 10, it's not bad. You can explain that to your manager.
Fortunately, I didn't have to. Okay, so basically that's all. So thank you for your attention. If you have any questions, then I'm happy to answer them.